It's very nice to be here with you. I want to say at the outset that the research I'm going to talk about was contributed to by many people. So I've always worked with teams of scientists and engineers, and there's several thousand people that have been involved in this. And in a sense, I'm a weak representative of this group, and mostly I commonly speak for the group because I'm the oldest, and not because I have any special knowledge. I like to say, and it's true, that if you see research that you might be identified as something that I did, almost always there are younger people involved, and usually one of those younger people's name is up front, and you give that person the primary credit, not me. I also want to say at the outset that I'm commercially contaminated. So you should think of me as commercially contaminated. I work hard to translate science that we basically generated in my University of California laboratory out into the world. I was permitted very generously by the university to leave the university twice on leaves of absence and found companies. And I still have an ownership share in those two companies, and I still play a substantial role in the business of one of those companies, and that's Positive Science Corporation. The second company is Both Scientific Learning, both California-based corporation. I've also recently co-founded a third company. The third company is focused on children that are, you could say, in the deepest trouble because of their neurological limitations or the alternate path to the brain is taken early in life. This company is called Stronger Brains. I'm not actually sharing in the profits of the company, but I'm very interested in what the company is doing, and I'm trying to promote what it's doing to everybody. So understand that I'm commercially contaminated. And finally, I want to say that I can only talk about a very complex subject, very superficially. So please think of this as a beginning or an introduction, if you're not familiar with the subject, to a very complicated science. So there's several 100,000 relevant manuscripts published in the scientific literature about what I'm going to talk about. Obviously, I'm not going to talk about this in a very deep way. So think of this as a sort of passage from a high altitude about things that are relevant to this complex subject. So I apologize for that, but there's nothing to be done about that, really. I'll do my best to try to make it meaningful to you. I want to say that in relation to autism, I'm a little bit of a fish out of water. This is not something that I've studied directly as a direct, although I've been interested in autism and the neurological curiosities or differences that are expressed in the brain of someone has one of the conditions that we put under the big label autistic spectrum disorders. One of the complications of talking about it is that it is a big pool of things. And there is tremendous variation across the population, across the spectrum, as we all know. And so it's difficult to talk about it without talking about specifics. In my mind, I think about specific extremes of autism on one end or the other in general. I've been involved in studies with autistic individuals, and they have been in these different extremes. So it's a little bit complicated to talk about this, but you shouldn't think of me as a true expert about autism per se. I want to talk about plasticity as it relates to conditions like autism. Our brains are continuously plastic. We have trillions of synapses in our brains. And these synapses are subject to alteration as a function of use. They can be enlarged, and their connections can be made more powerful. They can be weakened. They can disappear. They can sprout up for processes that are heavily engaged, and so forth. And this is a process that's with us for life. There's a lot more to plasticity than connective plasticity, as I'm going to talk about in a minute. But at the heart of it is the brain rewiring itself as a function of how we use it or engage it. It's the brain's big trick. We're continually remodeling our brain, continually revising it as a function of use. Plasticity is really about refining brain connections to serve our own useful purposes. You can think of it as being born with something like a roadmap of America, without any of the smaller highways or roads filled in, and gradually across life we fill in those highways and ultimately the local streets and ultimately the driveways and paths. What we're doing is elaborating our connectivity in our brains and specifying it. Basically, as we evolve our specific behaviors that define this operation, we actually create our operational powers. A little bit like being born with a factory that hasn't really figured out what it's going to make, what it's actually going to produce, and the factory actually creates itself. a function of how it progresses in life. It's an amazing thing. Through quite brilliance of moments of change, the machinery actually generates its operational powers and basically refines its operations in all kinds of ways that define what we can do and what we can't do in life. So we're all defined in this sense by this progressive plasticity. And it actually accomplishes three wonderful things. First of all, it's the basis of the brain's creation of each one of our own special models of the world. We actually create information and record it associationally. We basically define what goes with what. That ultimately leads us to the capacity to identify all of the things in the world and associate how they relate to one another across the dimension of time. We do this on an incredible scale, obviously, because we all have within us a construction of our world, incredibly elaborate, also very specific to our own individual history. Each one of us, because this process is so complicated, so elaborate, has created a machine within us that's unique to us. No one else has a brain. The detail is just like ours. No one else ever will. And of course, it occurs in rich variety. And there are many paths across this progression to create this complicated construct, and that lead in many different directions. The second thing, of course, is that it creates the self. It does this through a massive schedule of self-reference. So every time you feel, or every time you act, or every time you think, basically the brain is making an association, a second association. And that second association is the source of the thought, the action, or the feeling. And that association is you. So gradually, through billions and billions of self-associative responses, we actually create a physical entity that begins to establish agency. It becomes so powerful, there are actually 5 or 6 centers of this self-referencing report, largely in the frontal cortex and in the insular cortex in the brain. It actually becomes so powerful that it creates agency. It actually begins to take command of the ship. And ultimately, it substantially controls the expression of our thoughts and behaviors. This is all engendered within us, through a massive schedule of self-reference that occurs. It's all through physical and plastic change in our young lives. And one of the most amazing things to me about these processes is that we imagine, for example, when we see a child showing up at school, that everything's gone well, that the child is not very, very obviously impaired. We imagine that brain health basically is a given. Every child's doing a physical exam. Why isn't every child doing a brain exam? Of course, it's foolish to think that every child that shows up at school has a healthy brain. Clearly, as we continue and relates to the effectiveness of operations of how the child has gone through the process, creating himself and creating their operational capacity to this point in their life. It is also very obvious that a very substantial population of children that show up in school need help. Need help because their brain has been on an alternative path, or need help because the child has been experientially limited. Need help because the child's early life has been very stressful, very complicated in ways basically constrain the way the child can progress forward, move forward. And so one of my beliefs is that we have to get past this. We have to think every child comes to school, in fact, every child across the period of their life, as a work in progress, in which we should be continually monitoring to the best of our ability the status of health of the machine inside. And we should be doing what we can to make it stronger in every child. Certainly to make it stronger in children who are struggling early in life and across their lives. It's not just about defining the health, or refining the capacity of the child at some moment in life. It's about managing it. It's about taking care of it across the lifetime. You have to stop going to the doctor and the doctor asking the child, "How are you doing?" And Billy says, "I guess I'm okay." That's a basic annual health exam for the brain. It's nutty. That's irresponsible. And the third thing the brain creates, of course, is it evolves, creates specialization that accounts for all of the skills and abilities that define you. Every time you acquired any ability, like this child has acquired the ability to read, you actually created a reading brain. You have a number of brains, you could say, a number of you could say, machines in your brain that develop and have evolved, specialize yourself for everything you're good at. Your brain has done this over and over and over again. And it's defined you. And of course, it's defined you in modern terms, as you're a modern human. To a large extent, what you're good at and what you spend time doing in your life, in the modern life, is very bizarre from the point of view of the average human 100 years ago. Much less 1,000 years ago, much less 10,000 years ago. Well, the demands on the brain are very different. They're continually evolving. So what we require of a child now to be, in a sense, competent or operational in the modern world is substantially different, in many ways more challenging than it was 10 years ago, 20 years ago, 100 years ago. And it's continually evolving. It's evolving the presumption that our brains are good for everything. Even though we're actually changing our natures in a very fundamental way, by the way culture is evolving, by the way our tools are evolving. Imagine the brain is good for it. What that is, this, of course, is nonsense. But that's a special challenge for a modern kid to belong in the world. They have to be a modern kid. Modern tools are different than the tools you would apply. Not so very long. Now, it turns out that a lot of children don't develop a reading brain. About 15 to 20% never really do. And it turns out it's pretty easy to take most of those kids and train them for about 15 to 20 hours on the computer. And give them a reading brain. Reading brain now. Little activity centers, that posterior green square has actually an area where the brain is making the fundamental translation of word sounds by letter. More interior area activity is very highly correlated with language meaning words that are recorded in writing. So you can look down at the brain and you can identify 5 or 6 areas that are active in the brain of a reader, aren't active in the brain of a non-reader. It turns out that you can train a non-reader, and you can generate activities in these areas, in this more anterior area, this more posterior area. You see here, there's more excitement just below it. We know this occurs as with this translation of sound. The letter is occurring. We know that another 2 or 3 months it's going to be right up here, just as in a normal. But none of these children that actually been trained to read. They've been trained as listeners, improving the accuracy of their listening. Because most children that can't read, the fundamental problem is the listening problem. The problem is that the brain does not resolve the sound parts of words into the parts, the mnemic elements that are translated by letter. So for them, the translation makes no sense. They can't learn to phonetically. Because phonic, the letter translation is full of complexity and error. So they're frustrated. It's pretty easy to improve accuracy of the brain as a listener. You're training the child as a listener progressively on the computer. When you do that, basically the child recovers a reading brain. And in this case, every child that recovered that reading brain, documented in an imaging study, recovered reading to grade level within a year. So I want to point out this particular illustration just to say that when you think about the limitations of any particular individual, you have to think about them in neurological terms. You have to think about what it requires neurologically to correct them. Historically, we've been dominated in correction by thinking about them in psychological terms. Psychological terms, if we see a failed reading, what do we say? We can make this kid read. We can help this kid read. This kid can read. He can get it. It can get it. The solution is with reading. It's equivalent to saying, you're depressed. Let's help you by you not being so depressed. In other words, there's an obvious problem. And the obvious problem is a problem that obviously needs to be corrected. So historically, what we've done is we've looked at these problems from a behavioral perspective, primarily. And not that hasn't been useful to us, but incredibly useful to us across the complete history of psychology's nature. That is a positive contribution to the welfare of human people. But there's another, in a sense, deeper way to look at it. The real problem is a neurological problem. Every child, every individual in the world is limited in their operations as it relates to their life, in a sense. It reflects a neurological issue. We can think of their problems in this neurological sense. The question is, how would we approach fixing that? And often, the path to solution is not so obvious. The path to solution is not so obvious. So I want to talk about a key aspect of plasticity, because it's really important. And that is its reversible nature. But one of the first things that we did when we studied plasticity is we asked ourselves, well, can we drive the brain north or south? Or north and south? Well, we basically, in the brain of a monkey, had the brain, let's say, operated in a particular way representing the details of what the brain felt or heard. We said, well, can we refine this? And the answer was yes. It's easy to refine progressive brain. You can actually change the machinery of the brain in a way that improves that machinery, representing the details of what you see or heard dramatically. And really refine how it's resolving those inputs in detail, in fast time, in fast tick, in sharp tick. It also turns out to be just as easy to degrade it. Once you understand the rules that govern plasticity, it's easy to drive the brain south as north. I could take any one of you, and I could train you. And in 2 or 3 weeks, you would begin to lose your control of your hand. And in a month or so, your hand would be like a useless claw. Or I could turn that training around. And I could train you, and I could refine your use of the hand. You could do things with your hand you could never do before. Interpret things that you hold within it, or manipulation of it, those things and so forth. I could take you and train you in a way that within a month or 2 restores your ability to understand what I'm saying. Or I could take you and within a month or 2 improve your ability to understand what I'm saying, even under difficult circumstances. The brain is bidirectionally plastic. You say, well, why the hell would that be so? Why would the creator of the universe or Mother Nature give us a brain that's bidirectionally plastic? I'm going to talk about that more in a minute. I want to say that early in the science, we did a series of experiments like this. We said, can we make the brain resolve information when it's coming in and it's processing information at higher speed? Another way, can we change the operational characteristics of the machine so that it has a high sampling rate? Yes, you can do that. You can dramatically improve the sampling rate of the average brain. You can improve the sampling rate of even incredibly high sampling individuals, top ratings of them. Improve the sampling rate that resulted in him releasing the ball faster. I can tell you, no, not too many humans on planet Earth have a higher sampling rate in his visual operations than he does. Or you can turn it around, flip it around, and you can slow every brain down. Pretty soon it's only sampling information once every 200 or 300 milliseconds. You do 3 samples. Exactly. The process of the brain is bidirectional plastic. So about 10 years ago, with a wonderful young scientist at the end of Villers-Sudani, who's now an associate professor in neurology at McGill, and with Yogi Mishra, who's now associate professor in psychiatry at UC San Diego, with Xiaoming Zhou, who's now a professor in Shanghai, we began to ask a simple question. The simple question is, what is it reversibly plastic? I made a long list of initially 18 different physical and functional characteristics of the brain, looking focused primarily at the cerebral cortex. Ultimately, we've expanded on this to about 35 things, physical, functional, chemical aspects that relate in some elemental way to brain function or brain operation. We said, well, how many of these things are bidirectionally plastic? The initial experiments were very simple. First, we took animals that were really struggling, and we created two classes of animals that were really struggling. We either gave them very bad childhoods. I'll tell you exactly how we did that. We did very, very, very degraded conditions. Or, alternatively, we just looked at animals near the end of life. Looked at animals near the end of life, comparing both of them to an animal that's had a healthy early life and a private life as a young man. We looked at these 17 ultimately 35 things. We say, how many of these things are different? The answer is everything. Then we ask the question, well, how many things are different manage the animal that's had a struggling life? The answer is none of them. If an animal has really struggled early in life, everything is degraded. Everything we look at. The animal that's near the end of life, everything is everything. Then we ask the third most important question. How many of these things are reversible as specific forms of engagement in progressive training? And the answer to the second level of that question is how complicated would it be? And the answer to that question is everything's reversible. Everything. Now, just so you know, in an animal, in a rat, near the end of life, expected to die in a month or so, the reversal is almost complete. The rat looks almost like an animal in the prime of life. Everything is reversed, pretty much all the way back. And we see the same thing in an animal that struggled early in life. Everything is reversible. And it's difficult to distinguish the animal once it's trained from an animal in the prime of life. It has not had these early decisions. It is remarkable. Reversal of everything we look at. I just want to show you a few of the things that we looked at. This is very, very complicated stuff. So I just have to say, we looked at the physical brain machinery. We looked at new myelin formation. We looked at dendritic and axonal arbor branching, inhibitory neuron numbers and morphologies. Many columns is the basic processing units of the cerebral cortex and sizes and boundaries. All of these come back to the small size that we see in a healthy animal. Representational orderliness is recovered. In brain chemistry, we see trophic factor expression is back. We see receptor and subunit constituencies are like a healthy animal. We see modulatory neurotransmitter production and release is back. We see neurotransmitter transporters. We see blood-brain barrier integrity, norepinephrine expression, on and on. Everything's back. So repeatedly shown that specific forms of brain exercise grow brain power and restore neurological integrity. So here's a simple example. This is new myelin formation. This is in the old versus young trial, but we see the same thing in the young challenge versus young healthy trial. That is to say, a lot of myelin being made in the young brain, none being made in the old brain. It's being made again in the old trained brain. And if you just calibrate the training, you can make the old brain making just as much myelin as the young brain. This is blood-brain barrier integrity. This is an important issue for autistic brains because they leak. Blood-brain barrier is leaky. It's causing a whole series of problems. Basically, it's old. This is an old, not a young or autistic model. But you see it's leaking, and the green out in the tissue is leaking larger molecules, and then you train the brain, and it's back to the closure that you see in the normal animal. We've done subsequent studies in which we demonstrate we can close and open the blood-brain barrier at will, specific forms of training, and it's all reversible. This is the third example. This is a critical kind of inhibitory neuron, so-called human inhibitory neuron. You see there's lots of them in the young brain, not so many in the old brain, lots of them back in the old brain. And again, if it's trained, and again, if you just calibrate the training, you basically restore it to normalcy. Here's another autism-relevant example. This is actually an example from an experiment that was conducted in which a young brain was embarrassed. It was embarrassed by exposing the mother of the infant to antidepressant drugs. And when the baby's born, they have a big downregulation, among other things, in serotonin. Also, has a major impact on brain development. All of the things that we just talked about are down. We looked at about 15 of them. They were all down. And then we see that, you can see that expressed here. Here we're looking at serotonin recovery that's expressed by a transporter, the serotonin in the brain. We can look also at the serotonin-producing neurons. You see when the brain is trained, it's recovering. You see in the untrained animals way down, it's relatively little serotonin being produced, relatively little getting to the cerebral cortex. This is a part of a human inhibitory neuron. This is just a placeholder for a whole series of things we look at in these animals. You see in the control animal, it's high. Everywhere we look we're training the animal acoustically. We look at a second cortical area, a generalization of the impacts of this training all across the cerebral cortex. You see an impact in training. I'm going to see show in the center, in the somatosensory cortex. So this is the system we're training. You see it's recovering. This is the second system. You see generalization. Also generalization to the frontal cortex. You see in the sham animals, it's still low. So we can drive the brain back in a normal direction by appropriate intensive training in young adulthood. Note that the generalization of training impacts to the non-trained somatosensory cortex is something we see generally. So when we train in the visual system, train in the auditory system, we see substantial generalization all across the forebrain in things that are temporally related, time related. My time up? Well, I got about 19 more slides to go. Like I say, we can throw that plasticity switch up or down at will. And how does this apply to ASDs? Well, the training that restored brain health in these models was designed to progressively restore processing speed, attention control, and auditory neurotransmitter expression. And piecemeal studies indicate that a more elaborate training strategy could be effectively applied in this population. So 3 examples, 2 Asian and 1 contemporary. We've applied it with big impacts. Training children in listening, language listening, in studies that were conducted 20 years ago. And it's just shocking to me that these haven't been followed up with more intensive and more complete extensions because the effects were so positive and so impressive. 1.5 standard deviations in language ability improved by training children, on the average, improved by training children for about 25 years. I'd say it's and very, very powerful effects recorded in a whole series of other issues that relate to autism. But finally, we've been extending this by studies that have been conducted by a program that's called Stronger Brains, initially studied by the Benevolent Society in children that are unstable in foster care, can't stay in a foster care home. 5 or more homes in the previous year. Those are the children we trained. Trained about 200 of them. About 1/3 of those children identified as autistic. This is complicated. They're all across the board. They're just children that are so unstable that they can't be basically sustained in a home. What we see in these children is substantial recovery. They're all back stable in a home. By training them for 1 hour a day of the year, with a totally more combined, more complete training. A combination of motion training, motion system targeted training, social cognition training, cognitive training designed to restore the brain to normalcy, and help the child in a reevaluation by brain education. I think understanding that they are work in progress of substantial progressive advance. So I see a clear path forward for helping these children. I just wish that it could be get done faster. I'm now focused on trying to help Stronger Brains step on this path. I think there could be a lot more effort, a lot more application of this science applied to the benefit of these and other children that really struggle in the world. Thank you.